Seriously cool AI stuff. We've got this awesome Harvard CS50 lecture on how AI tackles problems, makes decisions, even understands stuff like you and me. So we're diving deep into that. Puzzles, games, you name it.
It's wild, right? AI can seem so mysterious, but really it all comes down to problem solving, and it all starts with searching for solutions.
Okay, so let's break down this whole search problem thing. The lecture uses that classic 15 puzzle, the sliding tiles. Can you walk us through that?
Absolutely. Imagine this. The puzzle's all jumbled up, right? That's your starting point. The solution, where everything's in order, that's the goal. AI takes that big goal and breaks it down into smaller steps, like different arrangements of the tiles. We call these states. Each move you make, sliding a tile, that's an action that takes you between these states.
So the AI is basically searching for the right moves to go from chaos to order.
Exactly. And think about it, this applies to way more than puzzles. Your GPS. That's solving a search problem too. Finding the shortest route, using locations and roads as its states and actions. But AI can handle way, way more complex situations.
Now, the lecture mentioned these nodes. Made me think of like a computer network, but it's something different here, right?
Good catch. Here, nodes are how AI keeps track of where it's been, like breadcrumbs. Each node is a state the AI has explored, along with the action that got it there, keeps it from running in circles, and helps it retrace its steps once it finds a solution.
So it's creating a map as it goes, instead of wandering around blindly. That's clever. But there must be different ways to search. The lecture talked about depth first and breadth first, which sound like totally different approaches.
They are. Depth first is like diving deep into one possibility, going as far as you can before backing up. Efficient if you're on the right track, but you might get stuck. Breadth first is more systematic, exploring all options one step at a time.
It's like making a big decision, right? Do you go all in on one option or carefully weigh all the possibilities? Sometimes that depth-first approach pays off, but sometimes you really need that broader perspective.
Perfect analogy. And just like us, AI needs shortcuts sometimes. That's where heuristics come in, basically. Educated guesses.
Like in a maze. Instead of trying every path, you use the Manhattan distance, how many squares to the exit to guide you. Not always perfect, but often faster. It's like choosing which lane to drive in. We use heuristics all the time without realizing it.
Exactly. And AI uses them in a similar way. But just like choosing a lane based on traffic miles ahead, heuristics can backfire if you rely on them too much. That's what the lecture called falling into the trap of greedy search.
So AI can be tempted by shortcuts too, even if they're not the best in the long run. How does it avoid those dead ends?
A search to the rescue. This balances those quick heuristics with long-term thinking. Still considers those educated guesses, but factors in the cost of the whole path, so it's not fooled by a shortcut that leads nowhere.
So it's like AI is learning to pause and consider everything before jumping in. Good lesson for all of us.
Absolutely. Now let's switch gears from puzzles to games. The lecture uses tic-tac-toe to show how AI tackles strategic thinking.
Tic-tac-toe. Sounds simple enough. How does AI go beyond just like randomly placing X's and O's?
It's all about understanding the game's structure. AI defines the players, the allowed moves, and what it means to win. We call this the utility function. It's like AI is creating the rulebook before it even makes a move.
So it's not just playing, it's understanding the game itself. Fascinating. What happens next?
This is where it gets really cool. AI uses what's called the minimax algorithm. It essentially looks at all possible moves and counter moves, assuming the opponent is also playing perfectly. Like planning your moves in chess, but on a way grander scale.
Whoa, that's some next-level strategy. But realistically, can AI actually consider every possibility, especially in a game as complex as chess? There have to be limits, right?
You're right. Exploring every single path to the very end is impossible, even for AI. That's where depth-limited minimax comes in. It basically sets a limit on how far ahead the AI calculates, a trade-off between perfect play and, actually being able to compute it, just like how we make decisions with limited information in our lives.
Okay, that makes sense. It's reassuring that even AI has its limits. But how does it judge who's winning during a game, especially if it's not a clear win or loss yet?
That's where the evaluation function steps in. It gives scores to different game states based on which player has the advantage. Think of it as awarding points for, controlling key areas. It's a way for the AI to evaluate its position strategically, even if the game isn't over yet.
So AI is like a chess grandmaster, always thinking several moves ahead. But we've been talking a lot about AI doing things, searching, strategizing. What about knowing things? How does AI represent knowledge itself?
That's a great transition. Let's
Yeah.
dive into the world of knowledge representation. And you know what? We're bringing back Harry Potter for this one.
Ooh, Harry Potter and AI. I am intrigued. What's the connection?
Remember that example about whether Harry visited Hagrid or Dumbledore? That's where propositional logic comes in a way to represent facts with symbols. Each fact, like it's raining, gets a symbol, and we use connectors like and, or, implies to create more complex statements.
So it's like AI has its own language for understanding and manipulating facts, kind of like how we use math.
Exactly. AI isn't just storing data, it's trying to understand and reason about it. Now, the lecture mentioned models and possible worlds. I'll admit, those sounded a bit intimidating at first.
They did sound pretty abstract. Can you break those down for us?
Of course. Imagine AI creating mental scenarios to test its understanding, like playing out different possibilities in its mind. Let's say AI knows if it rains, Harry will stay inside. It can create a model where it's raining and then check if Harry is indeed inside based on that.
So it's constantly testing its knowledge, making sure its conclusions hold up.
Precisely. And this leads us to inference AI's ability to figure out new stuff based on what it already knows. The lecture used, it's Tuesday, it's raining, and Harry will go for a run. Given certain facts, AI can figure out other things that must be true.
So AI isn't just a giant database. It's like a detective, putting clues together.
Exactly. It's not just about remembering, it's about understanding. And while the algorithm details are fascinating, the key takeaway is that AI can analyze information to reach new conclusions, much like we do.
Okay, that is seriously impressive. But how does this translate into, like, actually solving real-world problems?
Well, who doesn't love a good mystery? Think of clue the cards, the deductions. It's all logic in action, right?
Right.
And AI can represent all of that in its language.
So AI could be a clue master. Could it, like, actually outsmart us with logic?
It's definitely possible, and it goes beyond clue. Any logic puzzle, Sudoku, Kenkan, anything. AI's strength is its adaptability. The lecture even mentioned Mastermind, that code-breaking game. AI can handle that too.
Wow, AI is starting to sound like a super sleuth. But what happens when those logic problems get super complex, with tons of facts and relationships to keep track of? It can't be as simple as plain clue, right?
You're right, that's where it gets more intricate.
Mm.
The lecture mentioned conjunctive normal form and resolution. Now, without getting too technical,
Please spare us the jargon.
fair enough. Basically, imagine taking a jumbled mess of thoughts and making them neat and organized. That's what conjunctive normal form does for AI. Simplifies complex logic.
So it's like translating a messy handwritten note into a clear typed document.
Exactly. And then resolution. That's how AI uses that simplified info to prove if something's true or not. Like a logic lawyer, building a case, looking for contradictions.
That's clever. It's like saying, if I assume the opposite of what I'm trying to prove and it doesn't make sense, then my initial assumption must have been wrong.
Precisely. It's a powerful way for AI to reason.
This is all incredibly impressive. It sounds like AI is capable of some really complex thought.
And we're just getting started. The lecture even touched on first-order logic, which lets AI think about categories and relationships instead of just individual facts. Like the difference between saying all students love AI versus John loves AI. One's a general rule, the other's a specific case.
So it's moving beyond just knowing facts to understanding broader ideas. That seems like a huge step towards more human-like reasoning.
It is. And with that, AI can tackle even more sophisticated ideas, like there exists a student who loves AI. It's about building a system that can grasp the nuances of how we think.
This is blowing my mind. It's amazing how far AI has come in, like mimicking and sometimes even surpassing human intelligence.
And we're just getting started. What happens when we take these powerful tools, the logic, the reasoning, out of the textbook and into the real world, where things aren't always so neat and predictable?
That's a great question. The real world is full of uncertainty. How does AI deal with that?
That's where things get even more interesting. The real world, it's full of maybes, right? That's where probability comes in.
Probability. Like, what are the chances of winning the lottery? Kind of probability.
Well, yeah, kind of. But for AI, it's about dealing with uncertainty, saying how likely something is, even when we don't have all the facts.
So instead of saying it will rain, there's a 70% chance of rain, like our weather forecasts.
Exactly. AI uses those probabilities to make predictions, just like those forecasts. And there are some ground rules, like probabilities, they always range from 0 to 1.
So 0 means impossible, 1 means certain. Makes sense. even for us non-AI folks.
Exactly. And all those probabilities, they have to add up to one. Something has to happen, right? 70% chance of rain, 30% chance of no rain. It all balances out.
Makes sense. But AI can't just flip a coin to make decisions.
Yeah.
How does it actually use these probabilities in a, practical way?
Well, sometimes random choices can be helpful, but more often AI uses something called conditional probability. It's about how the likelihood of one thing changes based on another.
Okay, example time. That sounds like it could get complicated.
Imagine you're a doctor, right? You got test results, but you need to figure out how likely it is that your patient actually has a particular disease. Conditional probability lets you calculate that, taking the evidence into account.
So it's like saying, given that this test is positive, what are the chances the patient actually has this disease? We're refining our understanding as we go.
Exactly. And that leads us to a big one, Bayes' rule. It's like a framework for updating our beliefs as we gather more evidence.
This sounds intriguing, but also kind of abstract. Real-world example, please.
Absolutely. The lecture used predicting afternoon rain based on whether it was cloudy in the morning.
So we're using past data to make guesses about the future, right? Like, how often do rainy afternoons follow cloudy mornings?
Precisely. But it's not as simple as cloudy morning equals 80% chance of rain. Bayes' rule lets us factor in how often it's cloudy in general, how often it rains overall. It gives a more accurate prediction.
So it's combining what we already know with new info. Kind of like how we learn.
Exactly. And this applies to so much. Diagnosing illnesses, spam filters. It's how AI deals with incomplete info, just like we do.
This is fascinating, but we've been talking about single events. The real world is messier, right? Lots of factors at play. How does AI handle that?
Now things are getting really interesting. The lecture introduced random variables. Sounds complicated, but it's actually pretty intuitive. Think of rolling a die. The outcome, that's a random variable. Each face has a 16 chance.
Makes sense. But what about when you roll two dice?
Good point. Knowing the outcome of one doesn't tell you anything about the other, right? Those are independent. But a lot of times, things are connected.
Like if it rains, people are more likely to have umbrellas. Those are definitely related events.
Exactly. And we can use that conditional probability again to figure out the chances of someone having an umbrella given that it's raining.
So how does AI actually keep track of all these interconnected probabilities? Sounds like it could get messy.
Enter Bayesian networks. Think of them as a map of how different random variables are related. Each variable is a point on the map. The lines between them show the influence they have on each other.
A flowchart for probabilities. Like it.
You got it. And with these networks, AI can do something called probabilistic inference, figuring out how likely something is based on what we do know.
Okay, walk us through that.
Let's say we're trying to predict if a train will be on time. We might know the chance of rain, if there's track work scheduled, even if the previous train was delayed. The Bayesian network lets AI consider all that together to calculate the odds.
So AI is solving a giant interconnected puzzle, filling in the missing pieces with whatever info it has.
Exactly. And one way it does that is by considering every single possibility and its probability inference by enumeration.
But with tons of variables, that sounds incredibly computationally expensive. Like it would take forever.
It can, which is why there are more efficient ways to do it. The lecture talked about sampling. Instead of interviewing every single person, you take a poll to get a good estimate right. AI can do something similar to get an approximate answer without analyzing every single possibility.
Clever shortcut. So what other tricks does AI have up its sleeve?
One more cool concept is the hidden Markov model. This comes in handy when we're dealing with sequences of events where each one depends on the one before it, but we don't get to see every single step.
Okay, that one sounds a bit abstract. Real-world scenario, please.
Imagine trying to track the weather. Each day, whether it's sunny, rainy, whatever, is influenced by the previous day, right? But we might only observe certain things, like if people are using umbrellas. A hidden Markov model uses those limited observations to figure out the overall weather pattern.
That's amazing. It's like trying to crack a code using the little bits we do know.
Exactly. These models are used everywhere: speech recognition, finance, anywhere we need to understand data that unfolds over time.
Wow, we've gone from basic search problems to these mind-blowing probabilistic models. AI is way more capable than I initially realized. What other cool stuff does this lecture dive into?
We've seen how AI searches for solutions, handles uncertainty, uses logic, but what about finding the absolute best solution among tons of possibilities? That's where optimization comes in.
Optimization. So it's not just finding a solution, it's about finding the best solution. So
Exactly.
it's like not just finding a solution, it's about finding the absolute best one.
Right, exactly. Think of it like trying to find the highest peak on a mountain, not just any hill.
Okay, I can picture that. So how does AI even begin to tackle those kinds of problems?
One approach is something called local search. Instead of trying every single possibility, AI starts with one solution and makes small tweaks, see if it can improve things.
So it's like exploring your neighborhood to find the highest point before you go searching the entire mountain range.
That's a great way to put it. Hill climbing is a simple example of this. You're always taking the steepest path upwards, trying to reach the top.
But what if there are multiple peaks, right? You could end up at the top of a smaller hill and miss the real summit. How does AI avoid that trap?
Good point. That's called getting stuck in a local optima. One way to get around that is with a technique called simulated annealing. It's actually inspired by how metals cool down and crystallize. Sometimes you gotta make a bad move to escape a trap and find the absolute best solution.
So it's like taking a step back to get a better view, even if it means temporarily going down a hill a bit. I like that.
Now, the lecturer also talked about linear programming, another powerful optimization tool, especially for problems with real-world limitations.
Limitations like budget constraints, resources, that kind of thing.
Exactly, like a factory trying to keep costs down but still meet their production goals. Or a delivery company planning the most efficient routes but with a limited number of trucks. Linear programming helps find the sweet spot, the best outcome given those constraints.
That's incredibly useful, finding the best solution within the rules of the game. So what other optimization challenges does AI take on?
Well, there are also constraint satisfaction problems. These are all about finding solutions that fit a specific set of roles.
So like scheduling a meeting where everyone's actually free or solving a Sudoku, right? Those have very specific rules.
Perfect examples. And AI uses techniques like backtracking search to solve them. It's a systematic way of trying different combinations, and if a choice violates the rules, you undo it and try something else.
It's like trying different keys till you find the one that unlocks the door, but way more intelligent.
Precisely. And arc consistency, that's like checking if the key even fits the lock before you try it. Helps narrow down the possibilities even faster.
We've covered so much ground, from basic searches to these incredible optimization strategies. It's clear that AI is a problem-solving machine.
And we've only scratched the surface. There's a whole other side to AI that takes these problem-solving skills to the next level. Machine learning.
Ah, machine learning. That's the buzzword everyone's talking about these days. But what is it really?
It's about giving AI the ability to, well, learn from experience, to get better at a task without being specifically programmed for every single situation. The lecture focused on supervised learning, where we give the AI labeled data examples of inputs and their correct outputs. It learns to connect the dots.
So instead of giving AI instructions, we're giving it examples and letting it figure out the patterns.
You got it. Think of it like flashcards. You show a kid a picture of a dog, you tell them dog. They learn to associate the two. AI does something similar, but on a massive scale with way more complex data.
Okay, that makes sense. What are some examples of things that fall under this supervised learning umbrella?
One big one is classification, sorting stuff into categories, like your spam filter, deciding if an email is junk or not, or facial recognition, figuring out who's who in a photo.
Okay, that clicks. What about predicting things like housing prices or stock trends? Is that classification too?
Great question. That takes us to regression. Instead of assigning something to a category, it predicts a specific value, a number, like a price or temperature.
So classification is putting things in labeled boxes, and regression is like placing them on a numbered line.
Perfectly put. The lecturer used the example of predicting sales based on advertising. It's all about figuring out those relationships so AI can make educated guesses about the future.
That's powerful stuff. But with all this learning and predicting, does AI ever get things wrong?
Of course. One challenge is overfitting. It's like a student who memorizes the answers for a test but doesn't actually understand the material.
So the AI might seem super accurate at first, but then it bombs when it encounters something totally new.
Exactly. Gets stuck in its ways. The lecture mentioned adding a complexity penalty to help with this.
A complexity penalty. Sounds serious.
Basically, it encourages the AI to find simpler explanations that are more likely to work in different situations instead of just memorizing every little detail of what it's seen before.
So it's like teaching AI to see the forest, not just the trees. Find the general patterns instead of getting lost in the reeds.
Exactly. Another technique is cross-validation. It's like giving the AI a practice test. Train it on some data, then test it on a separate set, see how well it generalizes to new information.
Makes sense. So we've talked about learning from labeled data, but what about learning through experience?
Yeah.
You know, more like how we learn.
That's where reinforcement learning comes in. Learning by trial and error. Kind of like training up pet rewards for good behavior discourage the bad stuff.
Like teaching a dog tricks with treats.
Exactly. The lecture introduced Markov decision processes. Basically, you have an AI agent, like our dog, that can take actions in an environment. It experiences consequences and learns which actions lead to the best outcomes.
Can you give us a visual?
Picture a robot learning to navigate a maze. It can move in different directions, finds the exit, gets a reward, bumps into a wall, penalty. Over time, it figures out which moves get it closer to the goal.
Like playing a video game, right? You learn by doing, figuring out which actions give you points and which ones get you a game over.
Exactly. And Q learning, that's a popular algorithm that helps AI figure out the best action to take based on what it's learned.
So it's always learning and refining its approach. What other kinds of learning are there? We've covered supervised and reinforcement. What else is in AI's toolbox?
We've covered a lot, but there's one more key type of machine learning: unsupervised learning. This time, no labels, no right or wrong answers. We let the AI loose on the data and let it find the patterns and relationships.
So it's like we give AI a giant puzzle, but we lost the box, no picture to guide it. It just has to figure it out.
That's a great way to put it. One big task in unsupervised learning is clustering, grouping similar things together based on their characteristics. Imagine organizing your bookshelf, right? You might group books by genre or author. AI does something similar with data.
So instead of us telling it how to categorize things, it's discovering those connections all on its own.
Exactly. And this pattern recognition is used everywhere. Understanding customer behavior, analyzing medical images. The possibilities are pretty much endless.
It sounds like AI is capable of some pretty remarkable things. But how does it actually do all this? What's going on behind the scenes?
A lot of these incredible feats are powered by artificial neural networks. They're actually inspired by the structure of the human brain.
Neural networks. Okay, now we're getting to the really complex stuff. Are we talking about building, like, artificial brains here?
Not quite, but they are super powerful tools. Imagine a network of interconnected nodes, kind of like a network of roads, where each node is processing information and passing it along to others.
So like a team of specialists, each working on a different part of the problem.
Exactly. The lecture introduced the perceptron, the simplest kind of artificial neuron. It takes in info, weighs the importance of different inputs, then makes a decision based on what it's learned.
Like a tiny decision maker, weighing the evidence and making a judgment call.
And when you connect a bunch of these perceptrons together in layers, you get these intricate networks that can handle much more complex tasks. The lecture mentioned multi-layer perceptrons and an algorithm called backpropagation, which, well, let's just say it's even more complicated than it sounds.
I'll take your word for it. No need to get into the nitty-gritty math. But can you give us a sense of how these more complex networks actually function?
Well, imagine that instead of just sorting shapes by color, the network is now identifying different dog breeds in photos, or recognizing faces, maybe even translating languages. These multi-layer networks, they're the powerhouses behind a lot of the AI applications we use every day.
That's incredible. So are there different types of neural networks for different kinds of problems?
There are. The lecture touched on convolutional neural networks, which are specifically designed for image processing.
Okay, that one sounds particularly intimidating.
The gist is, imagine a special magnifying glass that can detect things like edges, textures, patterns. Convolutional neural networks break down images in a similar way to identify those key features. That's how they can recognize objects, faces, all sorts of things.
That makes sense. Giving AI specialized tools for visual information. What other specialized neural networks are out there?
Well, for anything involving sequences, like understanding language or predicting stock prices, we have recurrent neural networks. They have this cool structure that allows them to remember past information, which is super important for understanding context.
So it's like that they can read a sentence
Mm-hmm.
and actually understand how the meaning builds with each word. That seems crucial for, like, natural language processing.
Absolutely. And for even more complex language tasks translation, summarizing a long document, there are long short-term memory networks. They're designed to handle those longer-range dependencies in language.
It's like AI is developing a more sophisticated understanding of language all the time. Are there any other breakthroughs in neural networks that we should know about?
The field is always evolving, but one more type to keep in mind is the transformer network. These are particularly good at understanding the relationships between words in a sentence, all thanks to a mechanism called attention.
Attention.
Yeah.
So AI is learning to, like, focus on the most important words, just like we do when we're trying to follow a complex idea.
Exactly. And that's led to big advancements in things like machine translation and chatbots.
Wow, this has been an incredible journey. From the basics of search and logic all the way to these complex neural networks, AI is a truly fascinating field.
It really is. And as we create these increasingly sophisticated AIs, it's important to remember that they are tools. Powerful tools, but tools nonetheless. It's up to us to guide